Okay, so this is the third lecture on Chapter 8. In this lecture, we're going to be going over the central limit theorem. In the central limit theorem, if samples of a particular size are selected from any population, the sampling distribution of the sample mean is approximately a normal distribution. And as the samples get larger and the population is larger, the uh, it'll become more and more like the normal distribution, or the approximation to the normal distribution will increase. So if a population follows a normal probability distribution for any sample size, the sampling distribution of the sample mean will also be normal, which is we'll go over that in a little bit. And we'll also we'll look at the next two things in the next couple slides. Okay, so right here we have four different types of distributions. We have a bimodal distribution. We have a negatively skewed distribution because it's going towards the negative axis. Then we also have a uniform. And then we also have the positive because it's going that direction. So if we take a sampling distribution, say we have 100 individuals in this population. Okay, so we've got 100 individuals, and we take all the possible combinations of taking two people at a time. If you do that, we could calculate how many combinations they would be, but essentially you have all those different combinations, in lines inside of here. And then these lines all represent means of those combinations. And you can tell there's just a ton of lines. And so if you take two, a sample sizes of two, a bimodal distribution is going to look like this. A negatively skewed distribution is still going to be negatively skewed, but it's going to start to approach normality. And then a uniform distribution is going to be a nice perfect triangle. And then we have the positive distribution. Sorry, I dropped my pen. A positive distribution, positively skewed distribution, is going to still have that positive skew, but once again approaching normality. Then as you increase the number in the samples, you notice as you increase the number in the samples, the distribution becomes closer to approaching normality. None of these are quite normal quite yet. And then right here, as you go to 30, all of these are pretty much perfectly normal. So we've got the combination of 106 and combination of 130. And so as you do that, it becomes closer and closer to normal. So right here, this is a really important term to know. It's called the standard error of the mean, and we'll get to that in just a second. But something that's really important to note, which we have noted in previous lectures, is the mean of the population is always going to be equal to the mean of all of the samples. Okay, so if we literally sample every single possible mean, so right here we sampled every single possible mean, actually all of these, you sampled every single possible mean. The sampling distribution. So this right here, these are all sampling distributions, and the reason why these are sampling distributions is these are distributions of the mean of these samples. So this is a distribution of the mean of the samples of 30. Okay. And then this right here is these are all means of samples of 6. This right here is all means of samples of 2. So the standard deviation, okay, the standard deviation again is the average distance of in this case the samples, the sampling means from the mean of all of the samples. So you've got the mean of all the samples, which is also the equivalent to the population mean. So you've got the population mean, and this is the average distance of all the samples from the population mean. Okay, and the way that you calculate that, well, first of all, it is signified by sigma sub x bar, and you, in order to calculate sigma sub x bar, you take sigma, which this right here is a population parameter, and then you divide it by the square root of n, which this right here is the square root of the sample. Okay, so if you have 9 in the sample, sorry, that was horrible, 9 in the sample, and you have a standard deviation of, say, 18, then the standard error of the mean, or the standard deviation of the sampling distribution, is going to equal 2. So that's how you calculate the standard error of the mean, and you're going to be using that quite a bit. So make sure that you write that down. It's called the standard error of the mean. The standard error of the mean, and we're going to be using that quite a bit. Okay, moving on. This right here, we've got the population in a normal distribution. So say you already have a normal distribution. And with a normal distribution, any sampling distribution of the sample means will also follow a normal distribution. So even if you're just pulling 2 at a time, samples of 2 at a time, it'll still follow a normal distribution because it was already normal to begin with. Okay, if the population is not normally distributed, the sampling distribution of the sample means will approach normality, or approach a normal distribution, when the sample size is at least 30. Okay, so right now we're going to assume that the population standard deviation is known, which is really important because you've got a we're going to get into situations when the population standard deviation is not known, and so just make sure that you are aware of what to use at what point in time. But right now, when we deal with z-scores and z-tables, we are assuming that the population standard deviation is known. Okay, so to determine the probability that a sample mean falls within a particular region, you've got to use the following formula. Okay, so this right here is the z-score. We're calculating the z-score of the sample that we're taking. Okay, so say we pull a sample and we want to determine what is the probability of this sample occurring. So we've got the z-score right down here, and then right here, is this a population parameter, or is this a statistic of a sample? Okay, x bar is the statistic of the sample. Mu, right here, is the population mean, and then we have sigma, which is the standard deviation of the population, and then divided by the number in the sample. Okay, so moving on, I'm going to show you guys how to use this. So say, for instance, that we are at a cola plant. Let's just say Coca-Cola or Dr. Pepper, because we're at Baylor and everyone loves Dr. Pepper at Baylor. So we're at a Dr. Pepper plant, and for some odd reason they have bottles that are 31.2 ounces. Okay, so the mean amount of actual Dr. Pepper in the bottles is 31.2 ounces with a standard deviation of 0.4 ounces. So they've got this conveyor belt going, and the average amount that goes into every single bottle is 31.2 ounces, but the average deviation from that is 0.4 ounces. So at 8 a.m. today, the quality technicians randomly select 16 bottles. So this right here, this is the sample. So this is the lowercase n. Okay, then this right here is the population standard deviation. So that's sigma. And then this right here is mu. And then the mean of the sample, which is x bar, is 31.28. So right here you see x, I don't know what just happened there, x bar minus mu over 0.4 divided by the square root of 16. So 0.4 is sigma, or the standard deviation, divided by 4, or this 16 square root, which is 4. And so this right here on the top, this is the standard error. Going back here, x minus x bar from the previous lecture is the standard error. And then sigma divided by the square root of n is the standard error of the mean. In other words, it is the standard deviation of the mean distribution. So the distribution of all the means, it's the standard deviation of the distribution of all the means. So that's this right here is the standard deviation of the distribution of all the means, and then this right here is the standard error of the mean. So you've got 0.4 divided by 4, which is 0.1. Okay, in other words, 0.1 is equal to the standard deviation of the mean distribution, or the standard error of the mean. And then you've got the standard error right up here, which is, the standard error is 0.18. So 0.18 divided by 0.1 equals, you just move the decimal over, 1.8. So what do you do with this 1.8? Well, the 1.8 is a z-score. So what we're going to do is I'm going to grab the z-score table from our fancy little formula sheet. And you find 1.8. 1.8, remember we're dealing right now with a positive z-score. So this right here, the negative is, anything less than. So is what's in the middle, is the probability of what's ever in the middle. So 1.8, 0.0359 is the probability of anyone having a score or a value greater than 1.8 standard deviations from the mean. So this right here, the z-score, is saying the mean that he pulled was 1.8 standard deviations above the mean. Okay, so the mean of the sample that he pulled is 1.8 standard deviations above the mean, the population mean, which that's pretty unlikely. You've got a less than a 5% probability of, or really less than a 4% probability or 4% chance of that occurring. Okay, so you can see right here, this is 31.2, which is the mean, or mu. Then you've got 31.38. This right here is the mean of the sample. The mean of the sample is 1.8 standard deviations above the population mean, which this right here is the probability of that actually occurring. So if we say that there is less than a 4% probability of that occurring, that's a pretty small chance. And so what we can probably infer from that is that right now there's something going on with the machines where too much is being put into the soda bottles. So that is the conclusion of this lecture. I'd encourage you to make sure that you're really familiar with this before you move on, because we're just going to keep on diving deeper and deeper into this. So yeah, hope this was beneficial, and yep, just keep working at it.